self.new cell, type ECM. And here, cell field is just a reference to all the pixels in your simulation. Okay, so and here we are creating this pixel from this position to this position, in Y from this position to this position, and in Z we just set 0. So we're going to be, because we don't have Z dimension. And here you have to say which cell you're going to put in those pixels, and in this case will be the same cell that you created in the line before. And now we have to say exactly where this cell will be. So this kind of code can only make rectangles, or you can call this multiple times and make a different cell shape. So the X spans from 0 to 256. So let's do this from 0 to 256. Can also be, yes, self dot. No, I think it works because it never goes to the last one. It's just like the iterate index of lists. And now Y, I'll leave you to choose if you want to put on the top or on the bottom. So it's going to be either from, so in comp cell, the orange is here on the bottom left. So it can be either from 0 to 64 or from 72 to 128. So you choose where you want to be the ECM. Do you want your apical size to be like a, sometimes it just don't work. Okay. Well, you choose. That would be my choice. So let's, and of course you have to give a properties to the ECM. So you have to ECM target volume. And you can either calculate the volume and then assign, or you just can set equals to its volume, which you don't have to think, right? Okay. Sounds good, right? And then you have to assign the target volume, no, the lambda. And you can make either more stiff or less stiff than your cells. Let's make more stiff. What? I missed, oh yes, thank you. Lambda volume equals 10. Okay. So let me now play. Ah, it's there. It worked for me, and my choice was to have the ECM below. Now, I don't much like this yellow thing. I'll change the color. And I'll make my ECM gray. You did not? I did? It's here. Because, well, something has to, the way that boundary disappears by having something copy over it, right? So it's protected because there is no boundary. Because, yeah, it's true. And that would be a way to make a medium-like thing, because these cells can copy over it, but, well, here is a fixed boundary. Here's periodic condition. So the only way that it can disappear is by having these things here kind of going this way. So if you, yeah, so because of the configuration, you can get away without specifying target volume, because, yeah, it's kind of protected or shielded, which means that in your case, you have no volume constraint here and no volume constraint here, so it will be exact same properties except for the addition values with the cells. So if you run simulation, no, it's implicit here. When you assign those pixels to be this, to be belong to this cell, you already assign a volume to that cell. Once you draw it on the grid, it automatically gets a new volume. So here you create an object with no properties and no existence. Well, it has an existence, but not. Yeah, because, well, the idea of the object is there, but the object does not actually has existence. Here you can access on those pixels. Yeah. So here you're accessing the grid of those points, and then you assign those points to be equal to this cell. So you basically draw the cell. Once you draw the cell on the grid, CompCell already keeps track of what the volume of this thing is. That's why you can access that afterwards. If you do this thing before you draw the cell, then you'll be 0. Because you access it before having a volume. Before having existence in the grid. ECM is a cell object, because right now. No. Self is all the functions that you have in CompCell. It's not necessarily this cell or that cell. Make sense? Sort of, okay. So here my simulation is running. And one thing that I would like to do is make the cells elongated. So instead of have 64 here, I can make 128. And because they are bounded by the size, the cells will automatically extend. So let's try this, see if it works. Will it work or not? Or more or less? You tried? It worked? Yeah, more or less work. But the addition properties of those cells, there's nothing intrinsic in them that prevent them one of the cells of flipping to the side. That can happen. Okay. Well, if I keep pushing this a little bit more, this might not work. Right here, this happened. Why? Because for the cell, it does not make difference to be like this shape, other shape. Actually, it prefers to be like this because that minimizes surface. So it's not natural for a cell to be elongated like this. Okay? You first have to force an elongation, and also you have to add different properties of this to this and this to this. So that's why to have a stable epithelium, you need to create cells that have different domains, or safe not. So now we want to create those compartments. Okay, so what you can do, you can take advantage of your initial simulation, and because initially you know exactly where the cells are, And you can actually create the cell types inside. Okay. So and put on top and the bottom, you can. Do you prefer doing this way? You can also draw them directly. But you still have to go over the cells and make sure that they belong to the same cell. Let me show how it's done here. Okay, let's do this after we assign the volumes. What you can do, first get the center of mass of the cell. Okay. Okay. So because we want to know exactly where the cell that you're looping R is, and then we know that the cell is 8 by 8, so we can actually create, let's copy this, 2 lines here, and create an apical side. And then you create that from your center of mass minus 4 to the center of mass plus 4. In your y direction, you probably want to create from your center of mass. So the apical should be, well, in my case, should be on the top. So maybe I want to write the apical already right there. So apical center of mass. Two. And actually you have to be careful because when you specify these variables, right, they have to be integers. Because every pixel coordinating the grid has to be an integer number, cannot be a float. But the cell center of mass can be it's a float. So the one thing that you have to do, you have to take the int, convert this into integer numbers. Okay. And this you create my apical side. And then I can do the same thing now. Oh, this has to be apical. For the basal side. So the x still be the same range, right? From one side to the other. But the y now has to be different. It should be from I minus 4 to I minus 2. I just want to make a shorter compartment there. So if you did with the ACM on top, then you can actually just invert this to coordinate boundaries here. I'll leave this here and try to play my simulation, see if it works. Okay. Also let me make this. It didn't work very well. Yeah, they need volume. So maybe that's, so let's add the volume. So apical. I'm misusing the boundaries here. Not quite correct. So this again. Still not quite correct. The other thing is that I'll probably want to do this assign volume of the core afterwards. I draw the compartments because I draw the compartments on top of them. And it will be whatever volume I had before. So the error that so first I have an alignment problem. The things don't seem to be very well aligned. And I also have the terminal screen. No, I don't have an error in this sense. I have an error in terms of it's not drawing properly. Yeah. So it's not really getting the. So remember, the last thing is a. If you want to actually go to x plus 4 here, you have to actually add one more because it never goes to the very end. So you have to do this here. And the y, it has to be here, and then it has to be minus 1 here to actually get this. Let's see if this works better. So yeah, it works better, but it's not doing this for the very first cell, which I quite don't understand. Yes. So when you have a problem like this, print what's going on. So x0, y0, make a string here. And let's also print this two boundaries here, at least on the x, right? The y seems to be working. And you can stop, run once, and look at the terminal. Well, my terminal is thinking now. Here. 360. Ah, that's the problem. I went too far here to the left, so I got a -1 here for the first cell. Which explains that if you carefully look here, all those compartments that I created are a little bit off to the left, right? So I probably don't want to do this. I want to do, it's probably from a rounding error for this integer. So I probably want to do this. And then now if I stop, do it again. Ah, now it is, everything's aligned. Okay. So do you all got this? So now you have, I create all those 3 different cells for each one position, but they're all individual cells. They do not necessarily belong to one cell or the other. What we have to do now, we have to wrap each one of those components to tell CompCell that they are actually belong to a cluster of cells, and not each one is a cell itself. So if you remember from yesterday, when you create cells in CompCell, each cell has an ID. This cell has an ID, this cell has an ID, this cell has an ID, and they're all different from each other. But if you want to say that all those 3 compartments belong to the same kind of cluster of cells, you have to tell them to have to specify a second ID property that will be shared between them. So in addition to the cell ID, which is particular to every kind of domain that's specified in a simulation, you also have something else called the cluster ID, which by default in CompCell is exactly equal to the ID of the cell. But the difference is that this cluster ID can be modified. And what you want to do, you want to make all these things to be equal for a single cell in a compartment, which means that this whole entity will be treated by CompCell as a cluster of cells, and then all these compartments will be internal compartments of your same cluster ID object. So the way you do this in practice is the following. So here now you see what you're visualizing are the cell and the cell borders, okay? And I can say that my cell border color is white and my cluster border is yellow, okay? So, but let me make the cluster border to be black. But you don't see any cluster border because the cluster border is overridden by the cell border. So we have cluster borders here. So if I turn on the cluster borders, you see that every single compartment is a cluster by itself. Okay? Because all these objects have a unique cell ID and a unique cluster ID. What you want to do is you want to make the apical and the base compartments have the same ID as the core compartment that you use. And the way to do this in CompCell is the following. You go here below apical, CompCell 3D Python, and I think it's cell constraints. No, wait. Yeah, I have to see where it is. Ah, here, cluster ID reassignment. Okay, thank you, James. And then this reassigns a cell domain to a cluster ID. So here, want to do is want to reassign this cell to have the same cluster ID of the cell they're looping over. So here you want to see cell dot cluster ID. Actually, I don't remember exactly if it's lowercase, uppercase, but what I can do is go here cell attributes, and it has here the cluster ID. So, okay, now I know how it's written. Cell cluster ID. So what SCOM is doing is saying that besides assign all these properties to the apical side, I'm also assigning to the apical side this cluster ID, which will be exactly the same as the cluster ID of my core cell that you saw. Now I can repeat this command also for the basal side. And now all those three compartments that you draw will belong to the same cluster cell. If I do here and now play, stop. Okay, my choice of course was not very great. I'll make the cell border color to be black and the cluster border to be white. Okay. Okay, and now it's more visible. Now you can see that there was a difference. Now, everything that's bounded by the white boundary indicates a single cluster, and what is separated by the black boundary, which you cannot really see in my zoom in, but I can. Right. It's not showing. It's not really rendering there. But you can see now that all the compartments belong to the same entity because they all have the same cluster ID. Does it make sense? Okay. You click here on the configuration, and then you can choose the cell border color to be black and the cluster border color to be white. And just to be consistent with the thing that I drawn there, I want my basal side to be red or maraschino, okay? And I want my apical side to be green. Okay. So I can change the color scheme here. I just want to make it exactly as I draw on the border. So I apply this. Okay, now the basal side, which is red, is touching the ECM, and the apical side, which is green, is touching the other one. Okay. But if I play, things go wrong. Why? Why things go wrong? You have to define the adhesion properties of those things as well. So let's just first play with the adhesion. So right now, the adhesion properties of everything is all equal. Everything is equal to 10. And you probably don't want that. You have to choose adhesion values that actually will maintain your compartments in the right place. So let's forget about the internal context for now. Let's leave everything at 10. What's really matter here is the external ones. So what we want? Now it's good to make some kind of table and try to guess what these addition values should be. So let's go to the side. Now we have the medium, the core cells, apical cells, the basal cells, and the ACM, right? And here you can make medium, core, apical, basal, ACM. So you have already played with the cell sorting, right? So you already know more or less how it behaves. So what you definitely want, okay, the medium doesn't matter, right? It's 0 by default. And ACM with the ACM doesn't matter is, you never add this contact anyway because you only have one compartment of these two, right? Now, you want your apical to touch the medium, the way we draw before. So you want this contact energy to be high or low? Low, right? So you want this to be low. What else do you want to be low? You basically want to be low everything that you want to be in contact with, right? What? Apical and medium. Now basal to ACM. So basal to ACM we also want low. We can forget this because this is just a repeat of this. You can. So this is a symmetric matrix, so you can ignore everything that's under or below one of the diagonal. So you want this to be low and this to be low. What wants to be high? The diagonal wants to be low. Because you want to make connections with this low, right? So yes, also you want to be low. So you can have pairwise on the sides. What you want to be high? Everything that hides things that you don't want to let happen. Apical to basal, yeah, so basal and apical want to be high. What else? Yeah, but I think you don't want them to. I think you have to allow a little bit. So let's leave this as neutral. But definitely you want basal with medium to be high. You don't want to prevent any flipping, right? And what else? And apical, you don't want to touch the CM. So the CM and apical, you also want to be high. ECM and core, you also don't want. So we can also make this high. And medium core, you also don't want that to go there. So you also make this high. And now ECM and medium, they'll never touch each other, but you basically probably don't want that anymore. Okay, and now core with apical and core with basal, let's leave it like 10, should be okay. Does this make sense? So it sounds like too many parameters, right? But this is basically a table. And go to the drawing board and say what makes sense to keep this kind of configuration stable, and then you can more or less guess. So, and then you can say, well, unfortunately, the disadvantage of the XML is that you cannot define variables and place a variable here. You have to define each one of these values by hand. The advantage of doing the Python only code is that at the beginning you can specify age equals 20 and then just place age here and then you can. So that's why I always do my simulations Python only. The disadvantage of the Python only is that you cannot grab the CC3ML and just click and paste for you. You have to know beforehand what you want to know, because otherwise you have to, well, you can copy from another simulation, paste it, but you don't have this drop-down menu for the non-XML version of the thing. But basically, that's what you want to do. And we can choose your age to be, let's say, 20, or maybe even 25 to make it very strong. And let's make our low to be really low. Let's make it 5. And try to do that in one simulation again and see if you get a stable configuration. And then you leave those other two to be 10. No, we are using XML plus Python, so you have to type everything by hand. Okay. But if you have a Python only simulation, then all these will be written in Python. No, no. We have a stable continue now. Didn't work very well on mine. So it worked really well for the apical side, but not so well for the basal. That's because I made a mistake here. The basal with FSM should be low and not high. Let me try it again. You guys got this? It's everything's perfect. So I probably made a mistake. No. Okay, so what did I did wrong? Maybe here. No. Said by him. Okay, one thing that I can try to do, you probably want these things to be a little bit longer, right? So probably can make the cell target volume for the core to still be 64 8 by 8. In this case, we'll force the cells to increase. So let's try to do this. Now it's beautiful. I think that I cut too much of the core cell, and eventually for some cells is missed. And because we want more cells to be long, what I just made is I made the target volume of my core cell to be still 8 by 8. So it's still more or less squarish, plus the top and bottom compartments, and then I get this kind of, the cells automatically elongate.